This is a video for section 4.9, distributed loads. With this, basically we're going to be taking a distributed load, which looks something like this. Let's see. And then we want to reduce it down to a single, let's see. We want to, so this is on a beam. But basically we want to reduce that force down to a single resultant force. So all we have to do is, let's see, we have this, we have the beam. These are just the X and Y axis. And so then we just want to know how to figure out what that resultant force is going to be. Let's see, this is W of X. So it's pretty simple. I'm gonna share with you the main equations, and this would work for any shape. So it doesn't, like this one right here is pretty simple, where it's just a triangle. A lot of the ones we're gonna be doing in the class will be triangles or rectangles, so it'll be pretty straightforward. But I'm gonna give you the equation for all of them, so that if you ever encounter a different shape, you'll know how to do that. So basically, to figure out the resultant force, so we want to find the resultant force. We also want to find the centroid, or that position of where the force is. So for the resultant force, F sub r equals the integral along the length of W of X dx. And this is the loading function. This equals the integral from across A dA, which equals A. So basically the resultant force equals the area, and A is just the area, so the area under the loading diagram. A lot of times, so like in that example I showed you at the beginning, a lot of times they'll tell you W of X, and they'll tell you like at this point it's, I don't know, say 100 pounds per feet. So up at this top point it's 100 pounds per feet, it'd be 0 down there. And so we just have to figure out what the triangle is. So 100 pounds per feet, if we know what the distance is, then we can figure out what that area is under that triangle. To figure out the location of it, so that's just part of it, so that's given us the F sub r, but we also want to find the location of that resultant force. So for the location, so for that, and I'm going to give you again the general equation, so that we'll just call that X bar, that's that centroid. It's going to equal, or it's a centroid and just the X dimension of that centroid, but it's going to equal the integral across L of X times W of X dx divided by the integral along that length of W of X dx. And that equals the integral of A of X dA over the integral of A, or along A of dA. So that X bar is just a centroid. The X bar, if we're doing one that's a rectangle shape, it's not a very good drawing, but so it's just distributed like this, the same across the beam. The resultant force is just going to be in the middle. So the resultant force would be right there, and it would be 1/2 of that length. For the case where it's a triangle, so say it's something like this shape, We have that beam that's length is L. With this one, the resultant force, so it's a triangle, it's going to be basically 1/3 from the heavier part of it. So let's see, take this down. That distance would be 1/3. Oh, can't draw very well. 1/3 L. And this part would just be the 2/3 L. So it's 1/3 of that heavier part of the triangle. And that's basically it for the for figuring out distributed loads. Most of the ones we'll be doing in the class will be pretty simple. They'll be those either triangles or rectangles. And that's it. We'll do some examples in class.